Hey everyone, Professor Michael Scanlan here. So, we talked about Faraday, we talked about Oersted. Let's talk today about Lenz, L-E-N-Z. So, Lenz's law is kind of an addition to Faraday's law of electromagnetic induction. Let's refresh our memories on that one. That a changing magnetic field through a closed conducting loop will create or induce an electric current. Now there's a catch that we didn't talk about yet. Currents don't like to be induced. Nature, unfortunately, is really kind of lazy. Or maybe it's fortunate that nature is really kind of lazy. So that's where Lenz's law comes in. Whenever a current is induced via electromagnetic induction, that current, if we remember back to Oersted's work, all right, has its own magnetic field. So if I have a changing magnetic field through a closed conductor, it makes a complete circle or complete loop, that's going to induce a current. That current has its own magnetic field. This is Lenz's law. The field from that induced current is going to fight the one that created it. It's going to fight the initial magnetic field. Let me show you how that looks. So I've got my ring launcher. This is called a ring launcher. You saw this in the last video where we were talking about Faraday's law. And I put a light bulb over this and showed that the changing magnetic field through that light bulb's little coil was able to induce a current and light the bulb. I've got a ring of aluminum here. I'm going to put down there on the bottom. Now, when I flip the switch, remember, an alternating current is going to go through these wires, this coil, and that's going to create a magnetic field that changes direction. A changing magnetic field. Okay? Through this closed loop of a conductor, an electrical conductor, that magnetic field, that changing field, is going to create or induce an electric current in this ring. The current induced in this ring has its own magnetic field. And those two, the one from the current and the one from here, pretty much are going to duke it out. Watch what happens when I flip the switch. It's pretty cool. And you'll see why this thing gets its name. Pay close attention. The magnetic field from the current induced in the ring fought this one, and that exerted a force upward. Here is a ring I'm going to put on here, and I'm going to flip the switch again. Watch what happens this time. Nothing. There's a reason for that. Let me show you. Here is the ring that we launched first. Here is the ring that we just attempted to launch. Notice anything different? The one that actually went up is a closed loop. The one that just sat there is broken. Without a closed path, electricity can't flow, can it? If I cut a wire, don't cut a wire by the way, if I cut a wire, whatever the wire went to is no longer going to work. There's another demonstration of Lenz's law I'd like to show you. This one's pretty cool too. Now, I have an aluminum tube, okay? And I have two little masses. They're the same size, they're the same shape, and they're the same mass. All right, they're identical to one another, except one is a magnet, it's this one, right? Yeah, it's this one. And one is not, it's this one. So watch. One is a magnet, one is not. Now, aluminum is not a traditional magnetic material, okay? It's not what we would call ferromagnetic. So again, here is the magnet. I'm going to put this one down for a second. Here's the magnet, and here's the aluminum pipe. Watch. It doesn't stick in the least. So aluminum doesn't respond or doesn't attract magnets like other metals do. Specifically, iron is going to be a common one. Nickel, chromium would also work. Scoop my stool out of the way. So, I want to show you this. If I take the non-magnet, right, and I run it through this pipe, I'm going to drop it through the pipe, it's going to fall right out. If I take the magnet, and run it through the pipe that it's not attracted to in the least, will it just fall out? It's taking its dear sweet time. What happened? Well, as this one fell, just the non-magnetic one, it's just working under the influence of gravity. A little air resistance, but that's not much. It just falls like anything else would fall. This one, though, the magnet, is a changing magnetic field as it falls, or creates a changing magnetic field as it falls through this aluminum. Aluminum might not be magnetizable. I don't know if that's a word. Ferromagnetic, we'll say. But it does conduct an electric current. So as this magnet falls through this tube, right, it represents a changing magnetic field, and that creates a current as it falls in the tube, just right around where the magnet is. The current it creates fights this changing magnetic field and pushes up on it. So what does that do? That slows the fall of the magnet down. That, and the ring launcher, beautiful demonstrations of Lenz's law. That yes, a magnetic field that changes through a closed conductor will induce a current in the conductor. But that current is going to fight the field that changed it. And the force isn't always going to be up. It's going to depend on the situation. But there will be a force, and there will be a fight between the two magnetic fields. Thanks for watching. I'll see you in the next video, everyone.